Hello, this is the last video for the discussion about light and waves. It has to do with something called the Doppler effect. Actually, that's an E. And so the idea about this is if you've ever had a ticket, a speeding ticket, and you got picked up because of a radar gun, they're utilizing the Doppler effect, and it has to do with how things move and where the observer of that motion is. And so what this is, I'll explain it, is there is a shift in frequency for light or sound, or any waves for that matter, if there is relative motion between the observer and the source of the wave. And again, it could be light or sound. And so let's discuss this. First off, let's talk about relative motion. If there's a source right here of some type of wave, here's the source right here. So waves are coming through, and the observer is right here. Then the relative motion really could be the observer could be moving directly towards the source of sound or directly away, or it could be the source of sound directly toward the observer or away, or both of them moving directly towards one another or away from one another. In other words, to have this shift in frequency, I'll explain that in just a second, you must have it so that the motion's directly towards or away from one another, either from the source of the sound or light wave or by the observer of those waves. And you have, both either going away or coming closer together, or you can have it such that they're both moving. Now, if I have to be moving in that direction, meaning that I'm moving in a direction that is not directly towards or away, I won't experience any type of Doppler shift. And so there has to be that directly. Another way of saying this is radial motion. Radial means basically coming towards or away directly with one another. So another way to say this motion between, instead of relative, we can use something called radial. These pins are dying. Radial. So that's another way of saying that motion. But you get the sense of it. You have to go directly towards or away from one another. Now, when we think about sound waves, there's a shift in frequency. And so what is that shift? And so let's say that you have maybe an ambulance or a fire truck, and you have the sound waves coming at you, and I am out here looking at it and hearing it. Now, if it's not moving, it would have a set pitch to the sound, which is quite loud and obviously pretty high pitched. But it turns out that that pitch, how high or low the sound is, the tone is, will change if there's that radial motion. That's what the Doppler shift means. So how does it shift? If the source of waves, let's say, is going directly towards me, it will have a pitch that is higher sounding than what it actually is. So instead of just my normal tone, see if I don't hurt myself, it would have a higher pitch, if you get the sense of that. Just don't hurt myself there. Higher pitch. So that means larger frequency. So larger frequency means higher pitch. If it's going away from me, then the pitch will change also, but instead again of having more normal pitch of tone of voice, my pitch or tone of voice, it would have a deeper, hurting myself, deeper pitch, lower frequency. So a lower pitch or a smaller frequency. And that's how it is with sound. And so if you go on YouTube, you can find where you can hear that. Normally, if I was at school, I would have a source of sound that I would just, sit it there and let you hear it. And it would be really annoying, very loud, but basically a given tone or pitch. If I swing it over my head, as that source of sound comes towards you, it will sound as a higher pitch. But when it begins to move away from you, it will have a lower pitch. So you get this warbling of the sound coming from that device. I'm here at home. I don't have that source, so I just have to try to describe this. Now that is for sound waves. But the same thing happens for the idea of light, because light is a wave also. Light has this characteristic of not only being a particle called a photon, having an energy given by its frequency, which we talked about, but also as a wave because it has wave properties. And we've spoken about this before. It's something that Einstein discovered, that though we knew light was a wave from the 1800s because of its characteristics and the properties that light has, and those properties are wave-like, Einstein in the early 1900s, through the photoelectric effect, he said, also has the photon or particle nature too. But this is a wave nature. And so we continued speaking of the wave nature of light. So let me explain what this means. So again, Doppler effect is there's a shift in frequency for light or sound if there's relative motion between an observer and the source of the wave. In this case, let's say it's a star. So if I take a picture of the spectrum of a star, it'd be all the light of the star spread out into its respective wavelengths. And if I did that, what I would find, I'm trying to see if I can locate one. What I would find is all the colors of the spectrum of a star, all spread out into its respective colors for a star. I don't know why this is doing this. Come on, play. Okay, if I go back to the type of spectrum a star has, we talked about this on the last video, you would see all the colors of the rainbow, but missing dark lines. And you can see this slide in the PowerPoint because I've provided this to you on the Canvas site for your class. You can actually look at all these, maybe a little bit better than me, you trying to see it from the screen, but you'll see all the colors present, except some missing lines relative to some of the gases which are present within the star. And so if I could draw all the colors, and of course I don't have all the colors, I would have, let's say, the blue side over here and violet. I would have, maybe green, all the shades of green, all the shades of orange, yellow and orange, all the shades of red in here. But I would also, within this, I would also have missing colors. I'll just put down 3. Missing red, a missing aquamarine, and a missing violet. Now I want to remind you for the different colors, for red, that's large wavelength, but small frequency. Relative to violet and blue, so this is violet and blue, this has small wavelength, but large frequency. The difference of those two colors is quite a large change in wavelength between blue or violet and red. Another way to say it is that blue or violet has large frequency and the frequency of red is much smaller. So you have those relative things. So let's say that this is the star that's not moving. So this is not moving. So if I can measure the wavelengths of this red and the wavelength of this green and the wavelength of this violet, well, the wavelengths would be exactly what those colors are. And that's what people who study the spectra, the rainbows of stars, can actually measure. And so basically, when I say lambda sub 0, we call it lambda naught, NAUGHT, means the true wavelengths for those colors. Remember that symbol right there means wavelength. That lambda, we've talked about that before. Now, let's get the star moving. And so let's say that the star is moving away from us. And so here's the spectra again. I won't bother drawing in all the colors, but this is where the true wavelength of red would be, of green, and of violet. But because it's moving away, where we would actually see those 3 dark lines, we call them absorption lines because of the type of spectrum star produces, they're all shifted toward the red end, which is shifted toward lower frequency. They're all shifted roughly the same. So we get a shift toward the red end. We call that a red shift. And so that's kind of cool. It means that when we look at the spectra of a star and we measure the wavelengths, I'm just going to put this as just lambda red, lambda green, lambda violet. There's no sub-zero there, meaning that these are the wavelengths that we measure that have been shifted. So lambda is the shifted wavelengths because of the Doppler effect. The shifted wavelengths. That's the unshifted true wavelengths when there's no motion. So everything's been shifted. And so what's kind of cool is if all the spectral lines are shifted toward the red end, right away we know that a star is moving away from us. That's kind of cool. But now let's look the other way. If it's coming towards us, then if I took a picture of all of the spectra of the star, now all the colors are there, except the missing lines, and again, this is where the true wavelengths should be. In this case, when it's moving towards us, when we take the picture, we would find all the wavelengths of, all the spectral lines, the dark absorption lines, are shifted toward the blue end. And so in this case, it's shifted toward larger frequency, higher pitch for sound, basically toward the blue end for light. And so this is what's known as a blue shift. So what do? We take a picture of the spectra of a star or of stars. That's the rainbow of colors. And we use something like a little crystal to spread the light of a star out into its rainbow of colors, like that crystal hanging from your mirror from your car, spreading out the light from the sun. So we can see all the rainbow of the sun. And then what we do is we take a picture of it, and then we see where all the spectral lines are. If the star's not moving relative to us, meaning that we're kind of sitting there just not moving in distance toward or away from one another, just basically stationary, when we measure the spectral of the absorption spectral lines, wavelengths, they're the true values for those colors. But if we find out that a star is actually, here we are, here's a star, and it's actually moving away from us, we would discover all the spectral lines have been shifted. This is how they are because of the Doppler effect. And they'll all be shifted toward smaller frequency. For sound, that's deeper pitch. For light, is toward the red end. And so we call that the red shift. And so if stars' spectral lines are shifted toward the red end, we know that the star is moving away from us. But if we go ahead and we determine that all the spectral lines have been shifted toward the blue end, that means larger frequency. In sound, that means higher pitch. For light, it's toward the blue end. Then we know that the star, if this is us and this is the star is actually coming towards us. And that's kind of cool. So all of a sudden, when we use light with telescopes, we can see the stars are there, and we can look at them and know that they're there. We can look at all the different types of things in the universe using the light that we can see with, and that's good. But now what we can do is we can take light and utilize it to determine how stars are moving or other objects are moving. Red shifted means this, they're moving away. Blue shifted means they're coming towards us. And we could tell that by how the spectral lines have been shifted from their actual true location on the spectra of a star. They're not there. They've been shifted over. So one of the things that people measure is how much it has been shifted by. So the wavelength shift, this pen's about ready to die too. So the shift is equal to, I'm going to go ahead and put an absolute value, the true value minus the shifted value. That's the amount shifted. And basically, if it's shifted toward the red end, going away from us, if it's shifted toward the blue end, then moving towards us, and we can actually measure the wavelengths of these shifted wavelengths, and we can actually find how much has been shifted by. It's called the shift in wavelengths. And there's a term for that. It's delta lambda. That's delta just means, I'll just put it right here, delta means the change in. So delta lambda is the change in wavelengths because of the Doppler effect. So right away, just by looking at the spectral lines, what we can determine is that basically how they're shifted will tell us just what direction the star is moving relative to us. But the motion towards, away from us or towards us, no motion basically at right angles to us. The Doppler effect is not given by that motion. So there could be that motion also, but this does not provide that. Now, if I ask you, why does this happen? I can do a little experiment. Imagine I'm out in a pond and I have a stick, and I just, in that pond, it's very calm, and the surface of the pond is very smooth. And if I pound it with a stick, what will happen if that's where I pound it right there? So right there is where I pound it. Ripples would move out from there, and the ripples would move away. And if I kept going pound, 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 if I could draw carefully, I would get circles of ripples moving out. That'd be the first time I pound it, the second time, third time, and so forth. And if I can imagine, this is like, you know, waves, where that's the crest and that's a crest, then that distance would be given as the wavelength of my little simulation of waves passing through a medium. So as an example, it'd be like this. And you can see this. And so the distance between the high points, that's the actual kind of concentric circles, is constant. Because I'm just sitting there in my boat, or however I'm sitting in the water, and not moving as I pound it. So I pound it, a wave passes through. I pound it in a certain amount of time, and another ripple passes out. Same amount of time I pound it, a third ripple, and so forth. So that means the distances is constant between all the ripples as they move out. But what happens if I start moving? I'll see if I can draw this maybe a little bit better, but good luck with that. I'm not a very good drawer. As you know, guys, you suffer me. So let's say I've hit the water, and the ripple has moved out. And it's moved out a certain distance. Let's say it's moved out to here. Okay? But now I move in this direction to here, and I hit it out again. And that new ripple is centered on that point right there. So it's right here. And then I move out a certain more distance, same distance here, and I hit it again. And again, the ripple is centered right there. Now, if I'm observing, what happens is that basically as the wave comes toward me, if I could draw this carefully, my wavelength would be small. And so I would find, since the wave speed equals the wavelength times the frequency, if that gets small, the frequency has to get big, because the wave speed in water is always constant, or the wave speed of light is always constant. So that stays the same. So if the wavelength gets smaller, because as I move towards the observer, and this is the observer, the wavelength becomes smaller because of my motion in that direction toward the observer. My wavelength is small, my frequency must get bigger. For sound waves, that means the pitch gets higher. For light waves, it means it gets bluer. You know, it's shifted toward the blue end. And we have the blue shift. But over here, what we see, let me see if I can draw this. The waves get basically much bigger wavelength. So in this case, if I'm observing over here, and the source of sound or waves is moving away from me, then what happens is, again, my speed's the same, but my wavelength gets much bigger, but my frequency must get smaller. And so for sound waves, the pitch gets smaller. So it gets deeper, as for what I observe from the source of sound. Or for light waves, the light is shifted toward the red end. And so because of that, we get a redshift. Now, there's only one last thing about this, and it's really important. So what have we found so far? Number one, we found if we can look at the spectra of a star, and the spectral lines which are always there, those dark lines which are always present in the spectrum of a star, if they've been shifted away from where they should be in the star's spectrum toward the blue end, then we know that the frequency of those spectral lines are bigger or larger. And the only way that happens is if the source of sound is coming towards us. But if we measure basically the fact that the frequency is smaller, meaning the wavelength is larger, then the source of light would be moving away from us. Blue shift and red shift. And we can measure again the amount of shift by delta lambda. And that's really important. And what we have found, excuse me, is called the Doppler shift equation. Something very important. It's a very simple thing to measure that shift. We already know the wavelengths of all those colors. Even if they're missing, that color's missing, we know the wavelength of that. We can easily measure by taking a picture of the spectra of a star and measure that delta lambda, which again is just the absolute value. That means if there's any negative sign, we just strip it off, of the true value minus the shifted value. That if we can easily measure those two wavelengths, we can get delta lambda, the shift in it. And it turns out that the speed of it, of the star, is given by the speed of light times that shift in wavelength divided by the unshifted wavelength. So we know that. We measure that in the laboratory. In fact, a lot of you, if you've been in the class and not have to get out because of this wonderful experience we're going through with the virus, we would actually do this. We would measure true wavelengths of spectral lines. We know the speed of light, and we can measure the delta lambda, because all we have to do is measure the unshifted, the shifted wavelengths. All this stuff is relatively simple. When we put it in this equation, we can actually find how fast the star is moving towards us if it's a blue shift, or how fast is it moving away from us if it's a red shift. And so now, because of the Doppler effect, several things is true. By looking at the light of a star, we can see the stars there, and we can look at its shape and get a sense of what its characteristics are by looking at it. But if we go ahead and we actually spread it out using something like a crystal into its rainbow, and we can actually measure shifts in the spectral line's wavelength, we can tell if a star is coming towards us, blue shift, going away from us, red shift. We also can tell exactly how fast that star is going to move away from us or move towards us with that equation. Now remember, guys, the point of this class is not to actually do calculations. The point of the class is to determine how we can use an equation and what the equation means so that we understand how scientists in astronomy works. So if I ask you, why do we worry about the Doppler shift with stars? Well, we worry about it. Number one, it can tell us which direction is going, away from us or towards us. And we get that by how the spectral lines have been shifted in the pictures of the spectra of a star from where they should be, their true positions, which would give their true wavelengths. But we can also use that shift called delta lambda to put in this equation to measure exactly the speed that they're moving towards us or away from us. And that's kind of cool. So those are the big things you want to remember. So if I ask you, if you ask me that is in class, on what you could, basically, what could you ask me on the exam over this material, is I would say, okay, it's the star's coming towards us. What type of shift of it is it? Well, it's a blue shift. What does that mean about the frequency? If it's a blue shift, it means it's been shifted to a higher frequency or smaller wavelength. If the star is moving away from us, I could ask, what type of shift would be a red shift? And what does that mean as far as wavelength? It means the wavelength is larger, which means for frequency, it's smaller. Get that stuff in your head, take it step by step, and actually write it out in your notes. So you got it all related there. I've given to you multiple ways. I want to make sure that you understand this. And of course, what you can do is, if you have any questions, you can use the Facebook group that you're all linked to, or you should be linked to. And remember what that is? Well, it's the Prof. Astro Mike, CC Astronomy. And I've given that to you multiple places before. You should join us, because we do talk about things in astronomy. So ask me questions there, or you can email me. However you want to communicate to me so I can help you with this. Now, just the last thing about stars' motions. You know, stars are so far away. If we look for the length of our span of our life, I've got two stars, they would rise together and come together. And for the extent of our lifespan, which is fortunately not as long as we should have, the stars seem to be not moving relative to one another. But over time, and we're talking long periods of time, stars will move apart, or stars will move together and cross, and so the patterns of the sky will change. So if I was out on the Earth long ago during the age of the dinosaurs, several things would happen. Number one is that what I would observe is that some stars that were present in the sky then would not be there now, meaning that they probably died, especially blue stars. But also, what would happen is that the patterns of the sky, the constellations, the shapes where the stars are, would not be the same because they move. And so if I'm out here looking at the sky, and here's a star, the star might be moving in this direction. So that's the motion of the star. Now, I can break that motion into two motions. I can have a motion directly towards me and a motion directly across the sky at right angles to my line of sight. This motion right here is known as radial motion. And I can measure that radial motion with the Doppler shift because it's directly at me. Star could be going away, so that radial motion be in the opposite direction. So this could be measured by the Doppler effect, and we get that measured. So the velocity radial would be given in basically meters per second would be the unit. But this motion, which is basically just across the sky, this motion right there is known as a star's proper motion. And the star's proper motion is basically measured in effectively degrees that it moves per year. across the sky, and that proper motion's very, very small. The star that has the greatest proper motion, meaning that it's moving across the sky, is Barnard star, excuse me. Barnard was an astronomer who measured this motion. And Barnard star, even though it has the greatest motion across the sky, that motion is still many, many times smaller than the width of a full moon. So in the extent of our lives, it will actually move not a huge amount across the sky. And that's the greatest amount of one. So stars are moving at great speeds, and they do move relative to one another. The reason why we don't notice it is that stars are just so dang far away from us. And so it looks like stars don't move relative to one another. But they do. They have radial motion and they have proper motion. The actual motion is this direction, but we break it up into two. Look, if I'd be moving in this direction and that direction, it would get me out to where I would actually end up and indicate the true motion star. So just to be very clear about this, this is an indication of the true motion of the star. It's moving through the sky in that direction with some speed. So the arrow there gives the direction of the motion, and the length of the arrow would be related to how fast is it moving. So this is where the Doppler effect comes into it. We can measure the radial motion of a star that way. Okay, guys, so this finishes up then any thing we have to do with regards to kind of our discussion about light. Where we go to next now is to actually begin discussion of stars themselves. And so we start out talking about what do we see, and so that'll be the purpose of the next video. Hope you guys are good. I'll post this today, and I'll continue posting all week long with new videos. As we get closer to when the exam should happen, meaning that we're done with Unit 2, and that means you should be done with Study Guide 2. Remember that Study Guide 2 is posted at the Canvas site in the files region for your class, in case you don't have Study Guide 2. You should be working on Study Guide 2, getting it finished. I'll continue lecturing to give you more information that you need to finish that study guide with. Once we're getting close, and especially when we get into where I begin talking about the birth of stars, that should be basically the last topic of Unit 2. And we're getting close. So I can imagine having an exam in a couple of weeks. So be prepared for that. I'll announce that also very soon. I'll tell you how we'll do that exam as we get closer. Hope you guys are doing well. I'm here. Take care. Bye-bye.